All right, guys, we're here. Geometry with Mr. G again. This is coordinate geometry. Starting with number one here. Basically, what we're doing in today's lesson is we are proving that we know a quadrilateral and a plane. We're proving that the quadrilateral is either a parallelogram, a square, or a rectangle, a rhombus, a trapezoid. We're going to prove that they are those shapes based off of what we know on the properties of these different quadrilaterals. So, for example, number one, it says find the coordinates of the intersection of the diagonals of, and then we actually left it on the notes here, but example one and example two are both talking about parallelograms. So it's supposed to be parallelograms here. So let's say find the coordinates of the intersection of the diagonals of parallelogram LMNO. So I have parallelogram LMNO already plotted here with those vertices. So we want the coordinates of the intersection, right, of the diagonals, where the diagonals intersect. And if you know from your definition of a parallelogram, the diagonals bisect each other, which means when the diagonals intersect each other, they intersect each other at their midpoints. So it's going to look something like this. All right, let's go ahead and draw the diagonals. Let's go from O to M first. And do little dash lines here, right? There's diagonal 1. Here is diagonal 2. Right, and right here is where they intersect, and they bisect each other. So again, that means they intersect at each other's midpoint. So really, all we need to do here is use our midpoint formula. Let's see. Let's write that down because I know it's been a while since we've used it. Let's go. So it's x1 plus x2 over 2, right? Comma, y1 plus y2 over 2. And we're going to use this, okay? Technically, you only have to do this once, but in order to check your answer, it's probably good to do it twice. I'm going to do the midpoint of, let's do midpoint for M. Let's see, I'll do the first diagonal I drew, which was O to M, right? So midpoint for OM. Well, the midpoint for OM, well, that's going to look like, let's see. This will be my x1, this will be my y1, right? This can be my x2, my y2 up here. So I'll plug it into the formula. That would be 7 plus 0, let me make these parentheses bigger, over 2. And then 4 plus 0 over 2. And that's going to give us, this is going to equal 7 halves over 2, or comma 2. So that's the midpoint, right? That's the midpoint of OM. Now, if the diagonals bisect each other, then that should be the same midpoint for LN, right? So let's check. What's the midpoint for LN? So let's do a different color here. Let's do midpoint of LN, right? Midpoint of LN. Again, use the same formula. So this time using red, right? So this will be my x1, y1 up here. This will be my x2, y2. Let's plug it into the formula. We get 1 plus 6 over 0, comma 4 plus 0 over 2. Oh, this is supposed to be, let me erase that. I said over 0, but that's not right. That is 1 plus 6 over 2. Sorry about that. And then 4 plus 0 over 2. And this gives us 7 halves, comma 2. And you notice that the midpoints are the same. So the intersection of the diagonals would be 7 halves over 2. You can just box in one of these, right? I'll just box on this one. We knew it was going to be the same. It has to be the same because, again, the diagonals bisect each other in a parallelogram. So let's move on to example 2. Okay, so in example number 2, you got this. It says 3 vertices of, and again, this is supposed to say parallelogram, so this should be parallelogram here. Telling you it's a parallelogram, right? 3 vertices of parallelogram WXYZ are WX and Z. So they didn't give us Y. We're looking for a Y, right? Where is the vertex Y? The first question, or the first thing you might want to ask yourself is, what quadrant? What quadrant would we find Y? Just by looking at this, you know that it only makes sense that Y is going to be somewhere probably in this vicinity, right? It's going to be somewhere over here in order to close this shape and put that fourth point here and get the 4 sides of this shape, right? It's going to be somewhere in that vicinity that I circled in green there. I'm going to go ahead and erase that, but we know it's going to be over there somewhere, right? And that's actually going to be, that's quadrant 1. So I know it's going to be in quadrant 1. And then the second thing that you want to ask yourself is, go ahead here. Again, definition of a parallelogram at least says that opposite sides are parallel, right? That's our symbol for parallel. I mean, hence the reason why it's called a parallelogram. The word parallel is in it. Opposite sides of a parallelogram should be parallel. We're actually going to use that to help us find where y should be, okay? Now, something you might want to also note here, this quadrant 1, remember now, this up here I'm underlining, that gives us the order the points should be in, right? So W, X, Y, and then Z tells the order here. That's how I know Y should come next here. It's going to be somewhere in this vicinity over here, right? It always gives you the order in the problem when it names the shape. So let's do this. First thing I would do is I'm going to look at the slope of, let's do slope of WZ. Do slope of WZ, okay? So the slope of WZ, remember we use M to represent slope. The easiest way to find slope in a graph is to do rise over run. So if I start at W and I want to do rise over run, going from W to Z, well, I'm going to go down 1. So it's going to be a -1 for going down, right? And then we're going to go to the right, 1, 2, 3, 4, 5. So the run is 5. So the slope of WZ is -1 over 5. I know that the slope going from X to Y then, right, that's going to be the opposite side, has to be parallel to that. And if you remember parallel lines, right, parallel lines have same slope, right? Parallel lines are supposed to have the same exact slope. So look how easy this is. All I'm going to do is I'm going to start at point X, and I'm going to use that same slope, -1 over 5. So I'm going to go down 1, and I'm going to go to the right 5. 1, 2, 3, 4, 5. Boom. That should be point Y. So that's point Y, and look, we can actually draw the figure now, connecting those lines, and then connecting those points, right? And there's our parallelogram. So point Y is located at 2, 1. 2, 1. And that's it for number 2. So looking at example 3, it says graph the quadrilateral with the given vertices. We already have it graphed here. And we got a part A and a part B. Let's look at part A first. It says show that ABC is a parallelogram by its definition. And we're using the definition that opposite sides are parallel, right? So opposite sides are parallel. So that's the definition we're using here. So yeah, we're just going to look at basically find the slope of all 4 sides here. If I start with AB, right? Let's do AB first. Well, the slope of AB, if I do rise over run, let's start at A, it's going to be up 1, 2, so it's going to be 2 for the rise, over 1, 2, 3, 4, 5. So the slope of AB is 2/5. Now, we know by definition that the opposite sides of a parallelogram should be parallel. And again, parallel lines, right? Parallel lines mean same slope. So now let's find the side opposite of AB. Well, the side opposite of AB would be DC, right? Opposite means the sides that don't touch each other. So let's find the slope of DC, and they should be the same, right? Let's find DC, slope equals. Okay, so start at D. I'm going to go 1. Oh, I go 2 up. And let's see, 1, 2, 3, 4, 5. Good. 5 to the right. And the slopes are the same, right? That's good. Now, we're not done yet, though. I got to prove, again, opposite sides, right? So we proved that the top is parallel to the bottom, but now let's prove that the left side is parallel to the right side. So I'm looking at AD. Did not mean to have, there we go. Looking at AD, and the slope of AD is going to be, let's go 1, 2, 3 down, so that's -3, and then 1, 2, 3 to the right, so that's a +3. And -3 divided by 3 is just -1, okay? All right, so let's check the slope of BC now. BC, because, right, BC is the side opposite of AD, so these have to be the same. Let's see if these are the same. Let's starting at B, we're going to go 1, 2, 3 down, so it's -3 again, and then 1, 2, 3 to the right. So it's positive 3 on the bottom. And that also gives us a negative 1. So again, those are also the same. Opposite sides are parallel. Therefore, this is a parallelogram. So you can prove a shape is a parallelogram by, first bullet point over here, both pairs of opposite sides are parallel. Okay. ABCD is a parallelogram because both pairs of opposite, that's keyword here, it has to say both pairs of opposite, right, sides are parallel. Both pairs of opposite sides are parallel. If you just said both pairs of sides are parallel, you could be talking about AD and AB, right? And if you look at AD and AB, those are obviously not parallel. They touch each other, right? Parallel lines should never touch. So you have to say both pairs of opposite sides are parallel. Now, part B is essentially asking the same question. I want to prove that ABCD is a parallelogram again, but this time we're going to use the property that both pairs of opposite sides, so both pairs of opposite sides are congruent this time, right? Because by definition, a parallelogram, right, opposite sides are parallel and opposite sides are congruent. So now we're going to prove this is a parallelogram by looking at how long the sides are. And we're going to have to introduce an old formula of ours. I'm going to write it here. The distance formula. This is going to be, we can do x2 minus x1, don't forget the squared, plus y2 minus y1, don't forget the squared. Introduce that old-time friend to this problem here. So let's look at AB again. If I look at just AB, we've got, let's do this, right? Look at the top here. This is going to be x1, y1. This is going to be x2, y2. Let's plug it in. We get 2 minus negative 3. Don't forget the squared. Plus 5 minus 3. Don't forget the squared. And this double negative becomes a positive here. And if you put this into the calculator, you should get the square root of 29. And I'm just going to leave it as a square root of 29 because it gives us a decimal. So I'm just going to leave it as that. And again, the opposite sides should be congruent. So AB should be congruent to, well, the opposite side of AB is DC. So let's check out DC now and see if that's true. Let's set up DC. So DC, right? If I look at DC up here at the top, I'm going to do my x1, y1, and my x2, y2 up here. And let's see, plug it in. Let's see, we got 0 minus 5, don't forget the squared, plus 0 minus 2, don't forget the squared. And when you plug this into the calculator, guess what you get? Square root of 29. So good, they have the same length, right? And that's what we're talking about when we're talking about congruent. Same length, right? Distance right here. You're talking about distance formula, okay? Same length, same distance. So good. AB and DC are congruent, which is good. But remember, both pairs of opposite sides have to be congruent. So we're not done there. You have to also prove that AD is congruent to BC before you can say it's a parallelogram. So let's check those out. In the meantime, I'm actually going to erase our x1, y1s up here since we're going to have to redo it. Erase those. And let's try this. AD now. AD is going to equal, let's see, up here, I'll do x1, y1 for A, and I'll do x2, y2 for D. So that's going to look like 0 minus negative 3, don't forget the squared, plus 0 minus 3, don't forget the squared. This double negative turns into a positive again. You put that in the calculator, you should get the square root of 18, which is, again, that's going to be some decimal. I'm going to leave it as such since it gives us a decimal. We're just trying to see if we get the same number, right, on the other side here. So this should be congruent to, which side is opposite of AD? The side opposite of AD is BC. So now we're looking at BC here. So BC equals, and then so this would be my new x1, y1. This would be x2, y2. And if you don't remember from distance formula, it doesn't matter which points are x1, y1, or which points are x2, y2. You should get the same answer regardless, okay? But here we go. Let's fill it in. We got 5 minus 2. Don't forget the squared. Plus 2 minus 5. Don't forget the squared. And when you plug that into the calculator, you also get the square root of 18. So you say, hey, look at that. 2 checks. Both pairs, right? Both pairs of opposite sides are congruent. And that's good, right? Both pairs of opposite sides are congruent. So you could say, back up here at the top, in this little box up here, you could prove a shape is a parallelogram by both pairs of opposite sides being parallel or both pairs of opposite sides being congruent. You can do either one. You don't have to do both. You can pick one and prove it's a parallelogram by doing either one of those. Looking at that slope might be the easiest one. Takes a little less time, but distance formula is also easy. So on to the next one. Okay, so in example 4, it says, and this is already graphed, right, the points. Decide whether this shape, right, this quadrilateral, I want to decide, is it a rectangle, a rhombus, or a square? And it says give all names that apply. So it could be a rectangle and a rhombus, or a rectangle and a square, right? We got to figure out which ones all apply, or which of the 3 apply. So one way I'm going to start this problem is by thinking to myself, okay, what are some characteristics that are shared between some of these shapes? And the first thing I can think of is let's look at a rectangle and a square, right? I think it's pretty obvious by looking at the picture. We know this is not a rectangle or a square, but again, we're trying to prove it. A rectangle and a square have to have right angles. And right, if I'm looking at this shape, obviously these angles are not looking to be like 90-degree angles, right? But we have a way of proving that. We're going to prove that by looking at slope. So for example, I'm gonna find the slope of AB, right? Let's find the slope of AB first. You'll see where I'm doing here. And the slope of AB, let's do rise over run, is going to be 1, 2, so 2 up over 1, 2, 3, 4, 5, 6, 7, 8. So 2 over 8, which reduces to 1/4. So the slope of AB is 1/4, right? Now, in order to determine if this is a 90-degree angle, I'm looking right here, right? I'm trying to see, is this angle, see what I'm circling here? Is that angle 90 degrees? That's what I'm questioning right now. In order for that angle to be 90 degrees, AB and AD, those two sides, have to form a right angle, which means they have to be perpendicular. So the reason why I'm finding the slope of those two sides is because if I can compare the slopes, if they are opposite reciprocals, or you might know it as negative reciprocals, then that means the two lines are perpendicular and they do form a right angle. So that's why I'm looking at slope. Now let's find the slope of AD now. So in this case, the slope equals AD. I'll start at A. We go down 1, 2, 3, 4, 5, 6, 7, 8. So go down 8, which is -8, over 1, 2, which is less on -2, which gives me a slope of 4, right? And if you remember negative reciprocals, right? If I want to look at opposite reciprocals or negative reciprocals, you have to find, so like for example, 1/4, opposite of positive 1/4 would be negative, and the reciprocal means you flip it. So 1/4 flipped would be 4. So the opposite reciprocal would be -4, which means if this slope here, the one I'm circling, if that were -4, then these would be perpendicular, and there would be a right angle, and you could say it's probably a rectangle or a square. But in this case, the slope is not -4, it is a +4. Therefore, these are not opposite reciprocals, cannot be square or rectangle. Okay, which means it's probably a rhombus. Now, we do need to prove that it's a rhombus. So let's think about what we know about a rhombus. What we know about a rhombus is that it should have 4 congruent sides. So see where these hash marks, these blue hash marks I'm putting here? All 4 of those sides should be congruent, but we need to prove it. So let's prove it. I'm going to look at doing the distance formula again. And unfortunately, it's long and it could be grueling, but as long as you get down the how to do the distance formula. It shouldn't be too bad. You're just doing the distance formula 4 times for each side. So let's look at AB first. AB, distance formula here. Let's look at my points up here, right? So this would be my x1, y1, and B would be my x2, y2. So if I plug that into the formula, we get 6 minus -2, don't forget the squared, plus 8 minus 6, don't forget the squared. And this double negative becomes a positive. You plug that into the calculator, and you end up getting square root of 68, which gives us a decimal. So I'm going to leave it as square root of 68 for now. We're just trying to see if we get the same thing, right? If all 4 sides come out to the square root of 68, then we're in good hands, right? That's what we want. We want all 4 sides to be square root of 68, because then we can say they're all the same. Then we can say, hey, this is a rhombus. So let's look at BC. BC. Oh, I should do this in different color here. So let's do BC equals. And new points here. BC, so this would be my x1, y1, and C could be my x2, y2. Plug it into our formula again. What is that going to give us? It's going to give us 4 minus 6, don't forget the squared, plus 0 minus 8, don't forget the squared. And when you put that in the calculator, you get square root of 68. Okay, so far so good. 2 of the sides are congruent. Now we got to keep going. You have to do it for all 4. You can't just stop there. We have to check all 4 sides here. So I'm going to keep going here. Let's do, let's look at BC. Or not, I just did BC, right? Let's look at CD. C to D. So this would be x1, y1. This could be my x2, y2 up here. And in this case, we're going to get -4 minus 4, don't forget the squared, plus -2 minus 0, don't forget the squared. Put that in the calculator, guess what you get? You do get square root of 68. So far, so good. 3 sides are congruent. We still have 1 more side to check, and that is the side AD. So let's look at AD real quick. AD. Erase those. AD, so this would be x1, y1. D would be x2, y2. You plug it into our distance formula again, and you get -2 minus 6, don't forget the squared, plus -4 minus -2, don't forget the squared. This double negative turns into a plus sign there, and guess what? That equals the square root of 68. So you say, yes, all sides are congruent. Therefore, if this is a parallelogram with all congruent sides, that is the definition of a rhombus. It is a rhombus. You could go another step here. You could actually look at the diagonals as well. Right, there's the first diagonal. Here's the second diagonal. And the diagonals should be perpendicular to each other, right? So if I found the slope of AC, well, the slope of A to C is going to be, let's look at AC, right? It's going to be 1, 2, 3, 4, 5, 6. So 6 down over 1, 2, 3, 4, 5, 6. So 6. So that's going to be a slope of -1. And let's look at the slope of BD. These should be opposite reciprocals because remember, the diagonals of a rhombus are perpendicular to each other. They create right angles here in the middle, right? So let's see. This should be opposite reciprocal. It should be a slope of 1 because the opposite reciprocal of -1, which is what I got up here for AC, the opposite reciprocal of -1 is a +1. So let's see if we get a +1 slope here. Looking at, what is it again? BD. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's going to be -10 because we went down. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Good, -10. And a negative divided by a negative is a positive, so that means this is going to be a slope of +1. They are opposite reciprocals. Therefore, this is indeed going to be a rhombus. There you go. And that's example 4. Okay, so we're looking at example 5, last example for today. It says find the slope of each side. That's probably the problem. This is first thing is graph the quadrilateral, which I've done, and determine its most precise name. So we're trying to figure out the most specific name here. And when you graph it and look at it, it kind of looks like a trapezoid, right? But it kind of looks like it might be an isosceles trapezoid. The two sides, QB and HA, right? Those might be congruent. But we have to prove it first, right? So let's prove this. First things first, let's prove that it's a trapezoid by finding the slope of each side. The slope of QB, well, Q to B, let's do rise over run, is going to be 1, 2, 3, 4, 5. So it's going to be 5 up, that's positive, over 1, 2 to the right. So it's going to be 5 halves. Let's look at the slope of HA. HA is going to be 1, 2, 3, 4, 5 down, which is going to be negative 5, and 1, 2 to the right, so a positive 2. So there's your slopes for QB and HA. Now let's look at slope of BH and QA. Now remember, a trapezoid by definition, if this is a trapezoid, has to have one set of parallel sides, right? Has to have one set of parallel sides. So let's hope that BH and QA are the same slope. Because remember, in order to be parallel, you have to have the same slope. So BH is a horizontal line, and the slope of a horizontal line is always going to be 0. Remember Hoy, Vux, right? Hoy, Vux, this is a horizontal line, so you're going to be thinking Hoy, and the middle number or middle letter here always represents your slope, which is a O, or you can think of it as a 0. And same thing with QA, it's a horizontal line, so the slope is 0. So indeed, these two sides, the bottom and the top, right, I can add arrows indicating those sides are parallel. Okay, so yeah, now I can say, okay, this looks like a trapezoid. So part B here says BH is parallel to QA, right? BH is parallel to QA because their slopes are the same. Anytime you have the same slope, then they're parallel. Part C says HA is not parallel to QB because their slopes are, well, it's as simple as you think it is. HA and QB are not parallel because their slopes are not the same. They have to be the same to be parallel. So because they're not the same, QB and HA are not parallel. Part D says one pair of opposite sides is parallel. Therefore, or so, QBHA is a, right, we've been saying already, is a trapezoid. We know by definition that means this is a trapezoid. Now let's look at part E. You'll see I've already filled in part E a little bit. So I was trying to get a little ahead here. It says, it's usually say if there. See if any pairs of sides are congruent. Because we know it's a trapezoid, but is this an isosceles trapezoid? Let's prove if it's an isosceles trapezoid. Remember, if it's an isosceles trapezoid, the two legs, which in this case would be QB and AH, they would have to be congruent. So we're going to look at the distance of Q to B and the distance of A to H, use distance formula twice and see, are they the same? You'll see I already have QB written in. When you do the distance formula for Q to B, you get the square root of 29. And when you do the distance formula from H to A, you get the square root of 29. They are congruent. So I can actually add hash marks here, right here and here. And I know this is going to be isosceles, right? Now let's look at BH. It says find the length of BH as well. That's this next part here. Show where I'm at right there. Guys, BH, that's real simple. Anytime you have a line that's horizontal or vertical in a coordinate plane, just count the squares. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the length of BH is 10. And QA is going to be, well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So QA is 14. So there's your links here. Right, that's good. And then so part F says, because QB is equal to HA, right, the length of QB is equal to the length of HA, right, they're both square root of 29, square root of 29 when I did the distance formula. That means QBHA is more precisely called an isosceles trapezoid. It is an isosceles trapezoid. Then the last question, part G, says find the mid-segment of the trapezoid. And it gives you A, B, C, or D. Well, the mid-segment of the trapezoid is going to be the line that would go through the middle of the trapezoid. Now, it may not be so obvious to draw it in, right? If I drew it in, let's use red, it would probably be somewhere around here. You're supposed to, you can count the squares if you want and hope you get close. But there's actually a formula to this. If you remember the mid-segment formula for a trapezoid, the mid-segment formula for a trapezoid is actually base 1 plus base 2 divided by 2, right? That's the mid-segment formula. And we know what base 1 and base 2 are, right? The bases, the top and bottom, are 10 and 14, right? These are base 1 and base 2 up here. So if I plug them in down here, we're going to get 10 plus 14 divided by 2. 10 plus 14 is 24, and 24 divided by 2 is 12. So the answer is B. And that's it for today.